I'm going to talk today about transfer metrics. You already did it with Ido in the lecture, like the general concept. So I'm going to explain the derivation for like the simplest case, like to go through it very, very quickly. And then we're going to solve two questions from previous test, one from like 2015, one from 2019, I think, something like that. So you see how the questions look like. So for the 1D Ising model, or the worm,
maybe with black.
Yeah, but the black is not very good. Can you see that, or is that So for the 1D Ising model, we have the Hamiltonian with one coupling interaction between sigma I to sigma I plus 1 and some, let's call it B, and another term that derives from the magnetic field interaction. So we can rewrite this in a more symmetric form. You see in a second why that's helpful. So the interaction terms stay the same, and the magnetic field we write as sigma I plus sigma I plus 1, we factor half. So now, if we write the partition function, we have sum over all the possible configurations of sigma I, e to minus beta multiplied by the Hamiltonian. So we have beta j sum over sigma I plus 1, beta b over 2, sigma I plus 1. So if we open the summation over I, we get, so from the interaction term we're going to have sigma 1, sigma 2 plus sigma 2, sigma 3, etc. plus the magnetic field with sigma 1 over 2. Okay. Sigma 1 plus sigma 2, and so on. So let's define, for convenience, beta j is k. I think the purple is better. Can I keep writing the purple? So beta k we define beta j we define as k, and beta b we define as h. And now the partition function is e to k sigma 1 sigma 2 plus h over 2 sigma 1 plus sigma 2. So I take each term, the first term from each expression. This is multiplied by e to k sigma 2 sigma 3 plus h over 2 sigma 2 plus sigma 3, and so on until the last term. So this sum go from 1 to n, and we're going to demand periodic boundary conditions. So the last term in the sum going to be k sigma n sigma 1 plus h over 2 sigma n plus sigma 1. Okay. So now we can see why did we do this? Why did we write the Hamiltonian in this form? Because now in each one of those exponents we have something that depends only on 2 degrees of freedom. So this one in sigma 1, sigma 2, this one sigma 2, sigma 3, and so on. So we call this thing, as you I guess all will be done, this will be this is a matrix element of something called the transfer matrix. So this will be sigma 1 m sigma 2. So m is the matrix, the transfer matrix. So this will be the first matrix element, and this will be the matrix element between sigma 2 and sigma 3, and so on. So
And it's a matrix?
yeah, where this is one matrix element between two states. So sigma 1 and sigma 2 can have either one of two states, where either plus or minus 1 in that case, we later see cases where they can have more options. So we can rewrite.
רגע, זה צריך להיות h חלקי 2? כן.
Yeah. H חלקי 2.
לא,
Yeah. No, here I wrote it like h because
why?
this like because okay, look, if I look at what I have here, each one of the terms appear twice. So I divided it by 2, so I can separate them. It's fine. I just add and subtract maybe you missed when I said it, so let's write this here. So periodic boundary condition, sigma n plus 1, going to be sigma 1. So the reason we do that is all of that framework is going to work for the case that n go to infinity. So we work in ensemble with a lot of particles. So if n goes to infinity, so this Hamiltonian have infinite number of terms, but the effect of the boundary conditions in the edges of the system is going to be finite, because it's a finite boundary. So the effect is going to be finite, and the Hamiltonian is infinite. So we say it doesn't matter which boundary condition we choose. So we choose periodic ones because it's the easiest ones to work with. That's the justification. That's one?
Okay.
Yeah, because you have exponent of sum become multiplication.
אז למה כאילו זה כאילו ממשיך מכפלות פשוט, או שזה...
Yeah, this is like, so this is for sigma 1, sigma 2, sigma 2, sigma 3, sigma 3, 4, until n. So if I define, so we say we define a matrix element of sigma, let's call it sigma I and sigma j as that. So this is sigma I, sigma j plus h over 2 sigma I plus sigma j. So we can write the rotation function because we have this n multiplications. So this will be sum over still sigma I with the matrix element between sigma 1 and sigma 2, and then sigma 2 and sigma 3, and then sigma 3 to sigma 4 until sigma n and sigma 1. Now we want to simplify that. So the definition where we sum over all the possible options for sigma I, it means that I have sum over sigma 1 equal plus minus 1 and sigma 2 equal plus minus 1 until sigma n equal plus minus 1. So I sum over, yeah, it's okay with it. I sum over all the possible options for each sigma I. So now we can use something called complete sum, which means that I have a summation over all the possible values of, in that case, sigma I. And I know that each spin state is like a full basis. So if I have like plus minus 1, so you remember I can use it to have like a 2 by 2 basis. So I have like 1 0 and 0 1. So if I sum over all of the possible options, that thing gives me unity. So that's called complete basis. So now if we go back to what we wrote here, we see that, like, for example, for sigma 2, I have this expression in the sum, and I know that sigma 2, I have summation over all the possibilities, so that thing is equal to, so I use like that sum for sigma 2, and this gives me I, which means that this will be yeah, okay, I just find it. So each complete set. Why did I write? Sorry, this is complete set, not complete basis. So each complete set for sigma 2, sigma 3, and so on until sigma n going to give me m multiplied by I, and then eventually I only keep the edges, so the sigma 1 on that edge and the other that edge, because they're the only one that appears like brackets and not like the other way around. So each one of those give me contribution of m, and then the only sum that I left with is the one over sigma 1. Okay?
למה את מניחה שזה complete set?
אני לא מניחה, it is a complete set. You know what sigma 1, 2, and so on are. It's spin basis.
Okay.
So, like, because it's a normal spin, it's a half spin. You have two states for plus and minus 1. So you can say that, like, I have one state that's plus, it will be 1 and 0, and I have another that is minus, that's going to be 0 and 1. So you have sum over two options, and if you put it here, you just get 1. Okay, so now, so we know that M, the transfer matrix, is supposed to be a 2 by 2 matrix because we only have two possible states for sigma. So that's the only thing that can be. So it's a 2 by 2 matrix, which means it have two eigenvalues. So we call them lambda plus and lambda minus. So that's why. So we have lambda plus and lambda minus eigenvalues of m when lambda plus is larger than lambda minus. We don't say anything specific about those eigenvalues, we just say this. So now we can rewrite that thing as this is a trace of m to the power of n, because this is like the diagonal terms of m to n. And this we can rewrite as lambda plus to the power n plus lambda minus to the power n. So let's take lambda plus outside, so lambda plus to the power n, 1 plus lambda minus lambda plus to the power n. And because we said that n goes to infinity, even if lambda minus is slightly smaller than lambda plus, that term going to be negligible compared to 1. So where n go to infinity, this will be approximately just lambda plus to the power n. So we have for each transfer matrix that we soon going to actually find, we now know that the general expression for the partition function is relatively very simple. We know we need to find the eigenvalues, and that's it. That we have all of the information we need for the system. And now if we have the partition function, we can find expectation values, heat capacity, all the things we usually find with partition function. So now what we need to do is to actually find n. So we define matrix element in that way, we said we have 4 possible states. So we have 2 states for each spin, so overall 4. So let's find them. So sigma I and sigma j. So one option for sigma I equal sigma j equal 1, or sigma I equal sigma j equal -1. And the third and the fourth options are when sigma 1 is different than sigma j, which means that one equal to 1 and the other one equal to -1, and those two are equivalent because we see that this is symmetric around the, if we exchange between the two spins. So that includes the both matrix elements. Okay, so if sigma 1 equals sigma 2 equal 1, this is going to give us e to k plus, so we have h over 2, 1 plus 1, so k plus h. If they both equal to -1, we get e to k minus h, and if they're different, and if 1 equal to 1 and 1 equal to -1, we get e to minus k. So overall, m is going to be e to k plus h, e to minus k, e to k minus h.
How you make this matrix? How you make this matrix? I don't understand.
Okay, so we have 2 options for each state. So we have, let's choose like plus and minus, and plus and minus. So this will be plus m plus, plus m minus, minus m plus, and minus m minus. So this covers all of the possible options. Okay. So this is like the simplest Hamiltonian we can think about, basically. And now let's see what happens when we do something a bit more complicated. So of course, this is the matrix. You can diagonalize the matrix, find the eigenvalues, etc. if you want. Usually it's not going to have to, because the stuff that we're going to get are usually going to be much more complicated than that. So this is usually not part of that. So question number 1. So 2015 B. I think it's the first question, if I did the mistake.
From exam? It's from exam?
Yeah. So you're given this system. So we have sigma 1, sigma 2, sigma 3, sigma 4, and so on. We have coupling constant between all of the spins in the direction. This continue between minus infinity to infinity. So we have coupling constant between sigma 1 and sigma 3 called J1. We have one between sigma 1 and sigma 2 called J2.
J2 or sigma?
J2. And sigma 2 and sigma 4, J3. So this is also going to be J3, and also those will be J2 and so on. Okay, so first of all we want to find the Hamiltonian, and second we want to find the transfer matrix. So that's what we, the only thing we can do. So the Hamiltonian. Okay, so let's start with J1. So we see that J1 is going to connect all of the terms that have odd index. So sigma 1, sigma 3, sigma 5. So let's say that if we sum over all possible i's, this is going to have sigma 2i minus 1. And sigma 2i plus 1. Okay. Now for J3, which connect all of the even index spins, we're going to have sigma 2i with sigma 2i plus 2. So 2 for sigma. And for J2, it's connect all of the odd with the even. So we take sigma 2i minus 1 with sigma 2i.
Can you explain how you now, when it's odd and it's even?
You mean how did I decide that
Yes.
that's that? Okay, so if I want to connect all of the odd numbers, so I have like 1, 3, 5, and so on, I can just write like I and I plus 1 and say that like I is like I plus 2 and say that I is only like odd numbers.
Okay.
But then it's going to be hard to like compare it with the other expressions. So I want to be consistent with the summation. So if I take 2i, so for each I that I take 1, 2, 3, 4, it's only going to sum the even ones. So if I take out 1, or if I add 1, it's going to give me the odd numbers that correspond to each one.
הסדר משנה.
So in the Hamiltonian, no.
למה זה מינוסים?
Because it depends if like we can just define J1, J2, and I don't remember if it's defined in the question. I think it's probably does. That all of those are positive, and then the system is a ferromagnet. So we have to have like minus in the Hamiltonian. When we talked about Ising model, we said that like to have a ferromagnet, you have to have a minus something.
רגע, איך ידענו שהוא צריך לספור מומנט של חצי כדי לא לספור אותו כשל פעמיים?
No, we add the half when we wanted. We're going to do something similar here, but for now we just write the system as it is.
So in Ising model, it must put minus before the J.
Yeah, because in that case you have multiplication of two states. So if they're both in the same state, you're going to have less energy, which is the system, which is what the system wants to have. So if it's anti-ferromagnetic, it want to be in opposite direction, and then it's not fun. Okay, so this is the Hamiltonian, and now we want to build the transfer matrix. So in the case of Ising model, we only had multiplication. We only had coupling between sigma I and sigma I plus 1. So it was very easy to know which state we transfer from to which state. But here we have one expression that connects sigma 2i minus 1 to sigma 2i plus 1, and we have like each one of those give us something else. So what we're going to do, we have to define a bigger transfer matrix. So instead of go from like sigma I m sigma j, each state going to be defined by two spin. So we define like not a set unit, a block for, I need more colors. Wait. So we define a block by two spins. And now, one state will be defined by, for example, sigma 1 and sigma 2. And then we have the transfer matrix, and then we have sigma 3 and sigma 4, for example. So each state is going to include more degrees of freedom. So now the matrix is going to be 4 by 4 instead of 2 by 2. Okay? Now we still have a problem because we have, so for those two terms, we can define, we can take like sigma 2i minus 1 and sigma 2i and say that we transfer to sigma 2i plus 1 and sigma 2i plus 2. But the third term is going to like ruin everything because it's not symmetric between those two elements. So what are we going to do? We're going to rewrite it. So this equals to minus j2 over 2 so sigma 2i minus 1 sigma 2i plus sigma 2i plus 1 sigma 2i plus 2. So this is the same concept of as what we did with the field, with the magnetic field. So you see that this one, for example, corresponds to sigma 1, sigma 2. So it's interaction within the unit cell, like inside this block that I defined. And same for this one. So this is like an inner interaction. So you can kind of think about it as magnetic field from like mathematical point of view. Or you can just see that like I want to just make it symmetric, so I can write the matrix like that. You can think about it whatever you want that helps you understand it. So now I can rewrite this matrix element from sigma 2i minus 1 sigma 2i to sigma 2i plus 1 sigma 2i plus 2 is defined with exponent of, so first we have beta j1 sigma 2i minus 1 sigma 2i plus 1 plus beta j3 sigma 2i plus 2 plus beta j2 over 2 sigma 2i minus 1 sigma 2i plus sigma 2i plus 1 sigma 2i plus 2. Done. So you can see that I have, so the first interaction term connects those two, and the second interaction term connects those two, and the third term is like, so I have one for this one and one for this one, so overall it's symmetric for both blocks. Okay?
רגע, לא הבנתי למה הביטוי הקודם לא הספיק לנו עם מה שאמרת שם לפני כן. נכון היה לפני כן את הסיגמה 1, סיגמה 2, סיגמה 3, סיגמה 4. למה זה לא הספיק?
This is the same. It's the same as the 1, 2, 3, 4. I just wrote a general index.
ולמה אני צריכה את הביטוי השלישי הוא שם?
This one?
כן, למה פתחת אותו ככה?
Because I want to make it symmetric. Because if I only put that, it's not going to be symmetric for both sides. And I want the matrix element to be symmetric.
את רוצה שזה יהיה סימטרי לצורך כל האיברים שאתה הולך לעשות, עושה פה...
Yeah, because this one is only the state on that side. So it's like we had earlier like the magnetic field multiplied by sigma I. So I made it I exchange it with sigma I plus sigma I plus 1
שתחזור
with a
פעמיים
high.
כאילו.
So yes, it will be symmetric for both states.
כלומר, אם היו שם 3 סיגמות, אז לחכה 3 אלה.
Yeah, but then it's not going to be symmetric because we don't have 3 states.
איך לדעת
You
מי
can always add stuff and divide, but like it's depends what you want to do together.
איך לדעת מפה הוא שמאל ומפה ימין לצורך העניין? מי היה הקט ומי היה ברב?
What other option can you take?
לא יודע, כאילו ששתי העברות 1 ושתי העברות 2 יהיו משמאל וששתי העברות 1 ושתי יהיו מימין.
It still works. It can still work if you exchange between them. It doesn't really matter. This is still going to be the same because it's symmetric.
אוקיי, טוב.
You can also put like this one here and then here put like 2y plus 3 and 2y by plus 4. Like it doesn't matter. It just have to be like consistent with the general. Okay, so we have a definition of the matrix element. So this is a 4x4 matrix. We don't really want to calculate all of the elements, so I'm just going to do like some of them. So, for example, let's take the state where all of the spins are up. So we have plus, plus, and plus, plus. So this is going to give us e to beta j1, then beta j2, and then here we also, the same as with the magnetic field, we have a factor of half, but if all of those are plus, so this gives 2, and then we have plus beta j3. Sorry, I replaced the j2 and j3, but you understand. Let's take plus, minus, m, plus, minus. So now we have, so this is going to be still plus and plus, right? So we have beta j1, j3 multiply also those two states, so it's still plus, so beta j3, and then for j2 we have multiplication of this, which is going to give us -1, and this is going to give us also -1. So this is overall minus beta j2. And same way you can keep going for each one of the states, and then the matrix would be like so plus plus m plus 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 minus minus plus, and then plus plus minus minus, and the same for the rest.
Why not divide by 2? The last bj2, you not divide by 2 like this.
Yeah, because you have for that state you have that multiplication give you -1, and that multiplication also give you -1. So we have -2 over 2 overall -1. If I had like this would be plus, so that overall give me 0 because I have 1 and -1. Okay, so that was one question. It's not very fun, but like I think after you solve, just a second. After you solve like a few similar questions, you understand the general concept. Yeah.
Can you explain again how you get this explanation?
That. So. general, the partition function is e2 minus beta h. So h is given with that. We have e beta j1. So we have some overall I. So we have sigma 2i minus 1 and sigma 2i plus 1, for example. Okay, and then there are the rest of the Hamiltonian. So same as we did with the Ising model, I just didn't do it here explicitly because it's going to be too long. So that thing can be written as multiplication of the sum. So beta j1, sigma 1, sigma 2, plus beta j2, okay, so sigma 1 and 3, plus beta j2, sigma 1, sigma 2, and the rest, and then exponent of beta j1, sigma, sigma 3, sigma 4, and then for each of those 4 spins, like 1, 2, 3, 4, you're going to have like one exponent that's going to be defined as the transfer matrix. So in general, we're not going to do this derivation like from scratch. So if we say that like the exponent of the Hamiltonian within this block, those states that we choose is going to be the matrix element. Okay.
עוד משהו, שאנחנו נקרא קצת בבקשה?
רגע.
Which matrix?
אתה מטריד שמחק בדיוק לפני שכאילו שם.
With the plus minus.
כן, כן. למה לא יש גם את סיגמה באיברים האלו שמצאנו, של הפלוס פלוס פלוס פלוס? היה כאילו פלוס 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 זה אמור סיגמה 1, סיגמה 2, סיגמה 3 וסיגמה 4. קיבלנו את בטא J1 ועוד בטא J2 ועוד בטא J3.
Right.
את מה התכוונת? אתה רוצה שנחזור על זה כאילו?
אני לא מבינה מה השאלה.
השאלה שלי, למה לא קיבלנו, למה כשעשינו את החישוב נגיד לאיבר הכי שורה ראשונה, עמודה ראשונה, לא קיבלנו גם מה... כן, למה לא קיבלנו 4 איברים שמופיעים שם בארגומנט של האקספוננט שקיבלנו.
Okay, so we have plus plus and plus plus. So everything is plus 1. So this is going to give me plus and plus, so beta J1. This also going to give me plus and plus, so plus beta J3. Now I have beta J2 over 2. So this is going to give me plus, and this is going to give me plus. So this is 2 over 2.
Okay, so...
Okay. Okay, any other questions before we keep? Yeah. So, usually you have 2 types of transfer matrix questions. The first one is the more trivial type, which is just to find the transfer matrix. The second one, which is actually usually more common, I think. So you have a list of different systems, and you've been asked what's the minimal size of the transfer matrix. example, we saw that for the one-dimensional Isaac model, we have 2 by 2 matrix because we only have 2 states for sigma I. We saw that for the question we just solved, we have to define block that includes 2 spins. So we have 2 spins and each one 2 states, so overall a 4 by 4 matrix. So we're usually going to have the number of states of like sigma I. So it's usually going to be plus minus 1, but we're going to see cases where it's not the case, to the power of the size of the block. So we solved the case of like a 2-spins block with 2 states. So we had a 4 by 4 matrix. So let's see. So I start with one example that's actually not on the question, but just to show what are we supposed to do. So we have a Hamiltonian that looks like that. So we have minus j, and then sum over, so we have sigma I and sigma I plus 1, which is like the usual Isaac model. And then we have sigma I plus sigma I plus 2. So we have a nearest neighbors and a next nearest neighbors interaction. So this is going to look like, so we have this Isaac chain, I don't know, and then you have interaction of each one with the one next to him, and also interaction with the one after. So this is sigma 1, sigma 2, and so on. So what we want to do at that type of questions, we're not going to be able to usually to do this whole derivation like we did before, to write the Hamiltonian and then write the Hamiltonian in a symmetric way and then see like how we choose the parameters, because it's sometimes going to be, as we're going to see, it's sometimes just going to be too complicated. So we need to get like intuition. So if you want to guess, what's the minimal size of transform matrix we're going to need? So sigma I plus minus 1.
יש פה 3 איברים שבאים בקשר. נכון?
So ask it differently. What's the smallest size of a block in that, just visually, and that system that's going to include all the possible type of interactions? So think about what we did before. We had something like that, right? And like if I chose only one, this is obviously not a good choice because it's not. We see that it's not symmetric. So we took something that includes 2 spins, and then it's including this interaction, and this interaction. So we have everything. So if we look at that thing, we can also define 2 spins as a single block. So you can actually derive it by rewrite the Hamiltonian with like odd and even interactions. Surprisingly, it's actually more complicated than the example we saw before, because you have this interaction, like the nearest neighbors interaction, that's both inside the block and between blocks. So you have a bunch of interaction tests here. If you want, we can do it later, but the point is to try to like see the thing. So if it was like a different interaction, a coupling constant, so that would be J1, and that would be J2. So let's do J2 in red. So chose block that only have one spin. So, okay, we have too many lines on top of the other, so it's a bit hard to see that. But you see that it's not contain like if you want to write the description of the system with like this unit spin matrix. So it's not going to give us enough information because we have further interaction with more spin. Like just interaction between two spins is not enough. Each spin feel more than one spin next to it. So if I want to describe the interaction of spin sigma I have to include at least two spins. So this is the minimal size. I can always define larger transfer matrix, like that's the thing that, you know, I can always take like a 4 spin as a unit, but they're just going to be like too big. So that's why we ask for the minimal size that you can define. So you can try and think about like the minimal amount of information that you need in order to describe the system. So if I look at that spin, I have to have enough information about two spins at least to include all of the terms that appear in the Hamiltonian. Okay?
What the answer?
So yeah, so a block is to include two spins, and each spin can be in two states. So this is also going to be 4x4.
מה החלט מה הגודל של בלוק אחד? למה לא נגיד לך, יש 3 איברים לצורך העניין?
Because you don't need additional.
לא, אבל נגיד יש לך את פאי I, הם עושים טקסט עם פאי ועוד אחד, ויש פאי עושים עם פאי ועוד 2.
Right, but think about the usual one there as a model. You only have something like that. So you have interaction between two spins. So each block is one spin, and then you have interaction between blocks. Here, if you have a block that includes two spins, you can define the interaction as interaction between two spins blocks in that way. We can do it explicitly if anyone wants in the end of the tutorial. It's just a bit long and awkward. So we can come back to that if you want. It's just important that you try to like know how to identify it that way, because in the next ones we're going to do, you have like I plus 21 or something, so like stuff that you cannot do explicitly. So we need to try to understand the thing. Try to think about the example that we saw before with the squares. It's like an equation. Okay.
מה כתבת שם? מינוס J2?
Yeah, J2.
ומינוס סיגמה?
J2, just to have like, so this is like J1 and this is J2.
כן, יש גם סיגמה? מינוס סיגמה?
No.
אתה יכול להניח ש-I+2 זה מחוץ לבלוק עוד פעם?
If you only had that term, what would you say the minimal size of the block?
2.
No, why? This is the first model that we saw.
אז יש בלוק נגיד של 1 לצורך העניין.
Right. So I have the information. If I take a block with 1, it means that I have the information about two spins, because the transfer matrix takes me from sigma I to sigma j if I only have one spin block.
Okay.
So if I want to add additional spin to the Hamiltonian, I have to add additional spin to the state. So I have two spins and two spins for each block, so overall have interaction with two additional spins at least.
זאת אומרת, כאילו היה הופך להיות 4, כאילו בלוק יש למה 2 הייתי מצפוץ ספינס?
The block is 4, the matrix is, the block is 2, the matrix is 4. Okay, let's continue. So this is from the actual test. So the Hamiltonian you did with the Potts model, right?
Yes.
Okay. So this is like a disgusting version of that. So you have a delta of sigma I with sigma I plus 1 and delta of sigma I with sigma I plus 4. And the value of sigma I can go from 1 to until q. Q is just some number. Okay, so we don't care that what's the actual model. Like we don't care if it's like Ising model that we just multiply the spins, or if it's like a Potts model where we have like the delta of the two spins. We just care about what type of interaction. So what we have here, we have interaction of, again, each spin the neighbor, an additional interaction with the fourth neighbor. So this is plus 1, 2, 3, 4. Okay, so what's going to be the minimal size of the block now? This is very similar to what we did here. Okay, so if I take 1, it's obviously not good, right? I have a further interaction. So I need the minimal size, right? We need the minimal size that includes all of the interactions. So if I have something to go until I plus 4, so I'm going to need 4 spins to include that interaction, right? So I have a block that looks like that.
Not with 5 spins?
No, because look what we had here. Like if we had I and I plus 1, so we only need 1. If we had I plus 2, we need 2, and so on. We just need the rule is that we need the one that have like the longest range interaction. So that gives us the minimal number of spins that we need to include to know what's happening in the system. Because if we take 3 or less, every time we write the transfer matrix, it's not going to be able to include that interaction because we have to count until the fourth neighbor to have it. Okay, so we have block of 4. So this is one thing. We also need to take into account the number of states of the spin. So they gave us that the number of possible states is q. We have from 1 to q. So the minimal size of the transfer matrix is going to be q to the power of 4 by q to the number of 4, because we have q to 4 for each block. Okay.
Why we had 2 Qs?
Because one block have like 4 spins. With each spin can have q possibilities for the states. So all of the possibilities for one block is q to the power of 4. That's the number of different states. And the same way that we had for the Ising model, that we had 2 by 2 because each spin had 2 possibilities. So it's for each direction.
הסיבה שזה 4 זה משום שיש לך כאילו x1, 1, 2, 2, 3, 3, 4, אז כאילו בזה את צריכה 4, נכון? זו הסיבה שצריכה 4 איברים כאילו.
it's just because of that.
כן, כי בקשר 0, 1, 1, 2, 2, 3, 3, 4, כאילו יותר טוב.
Yeah, but even if you didn't have interaction between like 1, 2, and 2 and 3 and so on, you only had like that time, you still needed to have 4. The third one.
סליחה, in the first question is 2 בחזקת 2, או 2 בחזקת 2?
Yeah. Okay, so this one is also very similar. After a number of questions, you only can do so much with that. So you have sigma I with sigma I plus 1, and you have sigma I with sigma I plus 39. Because why not? And sigma I can be plus minus 1. So I'm not going to put like 39 dots on the board, but you already know the answer. So what's the number of blocks?
יש לך 40, נכון? 40.
No.
כפול משהו אבל לא סנטרס. יש לך 40 זה אחוז.
לא 40. 39. 39. So one block is 39 and we have two states, so 239 equal to 39. And the
because you have to... Where can I see 2 spins?
2 spins. No, not 2 spins. 39 spins. 2 states.
Ah.
Number of states to the side of the block.
Okay.
The combinatorial, so you can change each.
Okay.
So here the Hamiltonian is the same Hamiltonian, but so sigma I so the Hamiltonian is the same Hamiltonian, so we know the size of the block. But now sigma of an even index state, so sigma of 2i. Okay, so sigma if I is even, so for sigma 2, sigma 4, etc. It can be 1, 2, 3, or 4. So we have 4 options. And if I is an odd number, we have 3 options. So 1, 2, and 3. So we have like 2 different types of spins here. So if all of the spins only had 4 states, so we had 4 to the power of 39. But wait, I think I did a mistake. No, sorry, I did a mistake in the question. That's what happened when you do copy paste. Yeah, I need to remember to fix it. So okay, so we have one interaction term for the interaction between all of the odd spins, so sigma 2i minus 1 to sigma 2i plus 1, and another interaction term for the interaction between the even and the odd spin. So sigma 2i plus 1, sigma 2i, sigma 2i plus 1. So you have interaction between all of the odd spins, interaction between the even and the odd spins. So now the size of one block to include those two. Exactly. The concept is very similar to what we did here. And inside that block, we're always going to have one spin that is odd and one spin that is even. So the number of states going to be for each block is going to be 4 multiplied by 3, right? So the overall minimal size of the matrix is 4 multiplied by 3 and 4 multiplied by 3. So very big word.
Can you explain again why 4 divided by?
So if you have a block with size 2 and you had all of the spins could have 4 possible states. So you had 4 to the power of 2 multiplied by 4 to the power of 2. Right. But half of the spins have 4 possible states and half of the spin has 3 possible states. So for each block you have 4 possibilities for that spin and 3 possibilities for that spin. So overall you have 4 by 3 instead of 4 squared. Okay, so that was the question. And yeah, I think there are like a bunch of very similar concept questions in the test, so you can take a look or we put some in the homework. And that's it.
את בעצם אומרת מספר, זה המינימלי שאת יכולה להחליט, נכון? את בעצם רוצה לדעת מה מספר המינימלי שצריכה כדי לתאר בעצם מסע כל הקום שם. זה שלך, מה את תדמיין?
את המערכת.
אוקיי, כי את עושה את זה בקבוצות של אחד, כי זה כאילו הכי קרוב שאפשר לצורך העניין. גם אם אתה באמת צריכה את האחד עם זה. כי זה כאילו בלוק רציף, כי את רוצה ליצור בלוק, ובשביל ליצור בלוק צריך הולכת ליצור רציפה במקום.
לא, בלוקים של ספין אחד, בלוק של ספין אחד, אתה לא רוצה.
לא, כי כאילו כשאת אחד נגיד, זה בגודל 2, זה לא בגודל של עין, אז אמרת נגיד שצריך נגיד, אמרת לי, למשל, כששאלת לך שגם אם לא היה בעצם את האינטראקציה בפנים, עדיין לוקחת את זה בגודל של 4 לצורך מה שאתה אמרת, זה משהו שלא צריכה בלוק, לא תמיד אפשר לקפוץ בלוק.
כן, כי יש לי גם אינטראקציות